Good morning, everyone.
Morning. Yeah.
That's cool. I'm just looking up some stuff for photographic background on our topic today, which is galaxies, or actually, which is our Milky Way. More people coming in. Anybody have any questions before we get started?
Not really.
Not really. That's cool. Yeah, things are rolling along pretty well, I think. I am looking at some of the galaxies that are in the textbook this chapter. I was also looking up the Pinwheel Galaxy M101 that one of our students talked about earlier, making sure I knew where it was. The pinwheel is actually in Ursa Major. So, anyways, I was just pulling up some of those things. Sometimes I try to do that so I know the photographs up front, but I don't always do it in the proper time. So here we are. Oh, look, I got a tooth. This one, yeah.
Oh, special.
I'm sorry.
I got a tooth too yesterday.
Did you? This
Yeah.
one's permanent. I'm very excited about it.
I I get my permanent one in 3 weeks.
Oh yeah, yours is a crown though, right?
Yeah, mine's a crown.
Yeah, that's a much better process than the crap I just went through. Holy crap!
I just
You said there's a problem if it hurts when she's like screwing it in and unscrewing it and stuff, but yeah, my experience has been that yeah, there's a pain in each time. It's like electricity shooting through my skull every time she touches that daggone thing with the Allen wrench that she uses, and
oh.
I just ignored it and like, because otherwise she told me that if it failed again, that was it. She wasn't going to try a third time. So I just sucked it up and threw it in there. What I think is happening is I think it's actually hitting a nerve, and there's a galvanic process because of the dissolved ions in saliva and whatnot. So when you actually get two pieces of dissimilar metal, namely the part of the implant as well as the part of the actual tool, then those dissimilar metals are trucking ions through the ionic solution from the metal of the wrench to the metal of the implant.
Yes, the same reason why if you have metal fillings, you don't bite on a piece of tin foil.
Yeah, exactly. That tinfoil, you get that feeling. At one, it's a weird taste. It's a metallic taste, but then two, it's a electricity. Like almost, you feel like like your tooth is drawn to it or something. That's what's
Yeah.
going on with mine. So, anyways, I just ignored it. I said, "Oh no, it feels great. Go for it."
Fucker. Why would you do
So I said, "Well, that was the reason that you died, Mr. Younger. I'm sorry.
that?
Should have listened to this." Oh, all right.
Hell, man. Dirty pain? No, just keep going.
Just keep doing it.
Why does your face look red? This is my natural state.
Yeah, it's high blood pressure. Leave me alone.
I'm processing.
All right. Well, we're doing chapter 20 today, and I'm going to read over the learning goals, of course, for that because I'm playing the role of a real teacher the last couple of weeks.
You're playing pretend?
Yeah, I'm pretending to be a real teacher.
Oh, God. Oh.
Here we go. Let me start off by reading them. So this chapter 20, is called the Milky Way, a normal spiral galaxy. and it is normal. It's we think it's about 400 billion stars. However, the amount of light that it puts out is not sufficient to represent the amount of mass that it appears to have. So when we actually look at the total light coming from various parts, we get that basically our sun is something like 100 million trillion, or excuse me, our galaxy is like 100 million trillion solar masses, but or 100 trillion, excuse me. But when the mass is looked at by looking at the velocity curves, we get that it's that's only about 10% as massive as it should be. So that's where our dark matter comes in. But other than that, it's perfectly normal spiral galaxy. Okay. And actually, that in that sense, it is actually perfectly normal because we find that other spiral galaxies have exactly the same problem. Their luminous mass is way less than their uh, actual mass. And that's why we believe there exists something called dark matter. We're not really sure what it is. We know that it interacts gravitationally. It does not appear to interact with some other forces, maybe. So we're not really sure about that. And we know that basically 10% of the universe is something that we know of compared to the 90% of the dark matter. Okay, so that's like a 10 to 1 ratio between dark matter and regular matter. We'll later find out that there's dark energy, and that has a huge ratio too. That ultimately, what the stuff that we know of, the actual baryonic matter, as they call it, is around 2%, maybe very, very unlikely, but maybe as much as 5%. So somewhere between 2.8 and 5% of the universe is something that we understand. All the rest of the stuff is crap. We don't know what crap it is. So yay for that. Anyways, that is kind of exciting though to think that here we are. We've accomplished so much, you know, in the 400+ years that we've been looking at the universe with a telescope, which, you know, literally was a little bit more than 400 years ago. We've discovered a lot. We've discovered how long stars live. We've discovered what the matter is between the stars. We've learned that there's islands of stars that we call galaxies, that there's clumps of galaxies that we call clusters or groups of galaxies, and actually the bigger one is large as clusters and stuff like that. And we've learned that the universe seems to have had a beginning about 13.8 billion years ago. We've learned how it's going to end. We learned that our sun is about 4.5 billion years old, and it's going to live about another 4.5 billion years. So all that we figured out, that's really impressive. But it's cool that to think that we still don't know what, you know, 98 down to maybe 95% of the universe. So here's our learning goals. Explain how astronomers discovered the size and spiral structure of the Milky Way. Learning goal 2, list the clues of galaxy formation that can be found from the components of the Milky Way. Learning goal 3, explain the evidence for dark matter halo and for the supermassive black hole at the center of the Milky Way. So that's kind of cool. We got a supermassive black hole. Literally, we think it's about 4 million solar masses. Which is huge. Obviously, you know, if you use that little Schwarzschild radius thing, you're basically going to multiply 4 centimeters by, what was it, 3 kilometers is what we found the sun would be if it was a black hole. So that's how big the sucker would be. But lo and behold, the other spiral galaxies that we see have even huger or larger, I don't think huge is a word, more huge supermassive black holes at their core. And I'm talking thousands of millions of solar mass. So that's kind of cool. Learning goal 4 is the final one. Describe the local group of galaxy and how it offers clues about the evolution of the Milky Way. So what we're talking about here when we say this evolution thing is not only are we looking at the Milky Way for discovery about what it's made of, what's in it, where we are in it, how big it is, what's its structure. We're actually looking at it to figure out how it came to be and how other galaxies came to be. And, you know, that's kind of a big deal because we only make a lap around the galaxy about once every 250 million years. So that's actually the orbital period around the center of our galaxy is about 250 million years. So when we're doing that, obviously we don't get too many sights of it. We certainly haven't had a sight of an appreciable part of it now, because we've only been studying this stuff in a robust way for 400 years. And just around 100 years ago. Actually, I think it might be a little less because I think it was like 1921 is what we discovered last time. That we even knew that there were other galaxies. We thought we were the whole thing, right? The whole enchilada, but that's not the case. So, anyways, it's kind of interesting that we're looking at all that. I wanted to point out here's some cool galaxies that your book will bring up. I wanted you to understand that what they are as well as their names, just so we'd have an idea of how they're named and you guys could find them if you happen to luck upon getting an actual telescope or something cool like that. So this first one I'm showing you is Andromeda. I want you to notice that it's called M31. That's Messier 31. And the new general catalog, NGC 224. I think it's new. Now I'm starting to think doubt myself. But anyways, the NGC 224 is another name for it. This one is luckily named Andromeda Galaxy, so that tells us exactly what constellation it's in. If you look where Andromeda acts like two streams running off the corner of the Great Square of Pegasus, it's right next to the second pair of stars that are side by side. Out from between the two strings of stars and up above it. So that's a nice place. You can see it. If you are somewhere fairly dark, you can look at it with the naked eye and you'll see there's something blurry there. And it's pretty impressive because it's in the sky, its angular diameter is about that of the moon. So it's about the size of the moon when you actually look at it. And if you look sort of through the corner of your eye, then you can actually see it a little better, believe it or not. Another one that will come in contact with via your textbook is Messier 109, which you see is called Messier 109, but also NGC 3992. That's a barred spiral, and that is actually in Ursa Major. If you do a search for Messier 109, it'll actually show you within the constellation where you can find it. So you can actually look for that particular part of Ursa Major and look for it. Now, most of us have a northern, at least here in North Carolina, we have a northern hemisphere or northern horizon that's kind of crappy. It's screwed up with light. And that's also the case even at our campus at Virginia Beach. So if you're somewhere lucky where the northern sky is not that dark or not that bright, then yeah, you can check out Messier 109. But you can also check out, not this one, but this one right here, Messier 101, which is also called NGC 5447. This is the Pinwheel Galaxy. And you see that it does look like that photo that one of our students recognized as the Pinwheel Galaxy the other day. So I do think it is the same one. But there it is. It's beautiful. That also is in Ursa Major. So you can see it. It's from Earth in the constellation Ursa Major. Really a pretty constellation. This is a Hubble Space Telescope picture, so that's even cooler. And then there's this other one right here. This is an edge-on. So if you look early on in the book, they'll have a close-up of an edge-on galaxy. This is the galaxy that they're looking at. It's NGC 891, also known as Caldwell 23. It's called the Silver Galaxy and the Outer Limits Galaxy. This one happens to also be in the Andromeda constellation. So anyways, those are some of the cool galaxies we're looking on. Notice this dark disk right here. So what I was teaching you last time was that when you're trying to discern whether something is a spiral galaxy or an elliptical galaxy, if you see a disk of dust like this with these dark spots, chances are it's going to be a spiral, or it could in fact be an irregular galaxy that's being ripped apart by some other galaxy running through it, stuff like that. But generally, when you see a non-disturbed flat part with dark swaths in it, then chances are that's the dust disk of the spiral galaxy. Any questions on that? Okay. So let me now stop sharing my screen and start sharing my screen. So now I'm going to go to, okay, I will open this up. Not because I want to. In fact, this is what I covered last time in my other class. I'm just going to use it to open the other file. Well, let's just come open there in the background. That's weird. I just clicked on this thing and all of a sudden an extra window came open. I don't know why. Are y'all looking at a black window that says select a window or an application that you want to share?
No, we're looking at you. Hello? Anybody else here?
Yeah.
Yep.
Yeah, I think he just disappeared. Oh, he's coming maybe. Mr. Younger, you're on mute. Okay, there you go.
Thank you. Does anybody know what just happened? Like all of a sudden everything disappeared.
Yeah, you asked us what did we see, and we saw you, and after that, no one.
Okay, gotcha. Okay. Well, that was
Into a
exciting.
black hole.
All right. Well, what I'm going to do now is pull open the appropriate PowerPoint. Evidently, that was just too much for my computer, and it decided to say, I'm going to fart on you and disconnect this Zoom meeting altogether.
I'm going to fart on you.
Yeah, fart. That's
Official a term.
I'm briefing y'all on the most modern technological terminology of the day. Okay.
Gotcha.
All right. So I'm going to my PowerPoints, and I'm going to chapter 20. Which is right here, and hopefully we'll be able to see it now. Now, just to confirm, everybody's looking at PowerPoint chapter 13, right?
No.
No? What the crap are you looking at?
We're looking at you.
Dang it. Arr. I don't want you looking at me. Stop looking at me. All right, let's see. Nope, that's not it. Okay, so I can't share the screen yet because it's not there. Okay. Everybody, feast your eyes on my new tooth. So.
Go bite some tinfoil.
Oh, Lord, where is my PowerPoint? Come open. Okay, I see there's 19. Why is 19 open? Why is 13? Okay, 19 was open from the day before. Got that. 13 is open, yes, for that reason too. I'm waiting for 20 to open. It'll be really, really exciting when it happens. Okay, I might just have to go rogue and do it on my own, like a commenter. Have to open up my own applications, my own documents within my own applications, like a commenter. Oh, there it is. Okay, so now I'm ready to open. I'm going to do share screen. Let's see if it actually shows now. Stop getting in my way. Oh, there it is. Now I just said the window I chose to share is invalid. What the hell's a window invalid? Don't make me angry. Okay, come in one more time. Let's try this time. 3 times a charm. Or 12 times, whatever we're on here. Okay, yep, we got it this time. So everyone now sees not me, but rather, well, probably sees me too up in the corner. But hopefully you are seeing chapter 20 PowerPoint slides. Yes? I see the green frame around. The green frame doesn't always show for me, so when I don't see that, that's why I ask you guys what you're looking at.
Yes, we see it. We actually see it.
Oh, yeah, I get the green frame, but do you get the green frame too, or just this?
No, we got the textbook. That's it. We saw
Gotcha.
a bit of your desktop, which is messy, but.
So those of you who haven't been lucky enough to go somewhere really, really really dark. I don't know what that was. Really, really dark. Have never seen this cool image, but this is what the Milky Way looks like if you're somewhere really, really dark. And in fact, this sky is way brighter than it really should be. This is my guess is it's a time exposure because these stars are not stars. They're not pinpoints. They're actually little blurs, which tells me that they kept the aperture open a little longer than normal. If you look in this particular area, I wonder if we could find Sagittarius, because I suspect this looping part right here is actually the center of our Milky Way. But I don't actually see the stars well enough to see if Sagittarius is there. Then again, I also see stuff like this little blur and another blur over here that make me think that maybe this is a southern hemisphere photo. The main thing is that's what we're talking about when we see the Milky Way. You'll see a dark band that doesn't necessarily run, parallel to our equator. It actually runs at quite a different angle to it, and it'll have dark spots, and then it'll be surrounded by bunches of stars. Like literally, you see tons and tons of stars next to dark spots. So that's and Carl Sagan coined it the backbone of the night. But that's the actual Milky Way galaxy. I tell my students when they're in my kids, basically, when they come to the planetarium and I do shows for them, I tell them we're like a blueberry and a blueberry pancake. And when you're a blueberry and a blueberry pancake, you can either look at the pan that's cooking you, you can look at the woman that's cooking you, or the mom or the dad or whoever that's cooking you, or you can look at the batter. Okay, so this is the batter of the pancake. And I think that analogy works pretty well. Of course, you got to stay out of the sticky wickets, like, mom cooking for you or woman cooking for you, because obviously that's just riddled with sexism.
Didn't you just say person?
Yeah, no, I can't do that. That's a word I'm not familiar with.
The cook.
The cook. Yeah, there you go. The cook. I think that's classist of you to say cook. Anyways, so here's a picture of the Milky Way galaxy. We see the Milky Way as a bright band across the sky. It's difficult to determine the structure of the Milky Way from our position inside. You can imagine if you are a blueberry, for instance, in a blueberry pancake, how hard is it for you to tell what part of the pancake you're in? Am I dead center? I mean, I feel like I am, because everything seems to revolve around me. Am I near the edge? Well, probably not, because I suspect if I was that close to the edge, I could probably see beyond it a little bit, and I don't see that. So, that is the big deal. How do you find out? And prior to Shapley and other people, we actually had made a sort of grist mill model of the galaxy, of the universe, really, because they didn't think the universe extended beyond our galaxy. They didn't think in fact, in terms of galaxies at all. They just thought that all the stars we saw were all the stars, period. And they basically took the distance they could look in every direction and measured that, and they made this giant gristmill looking thing, and that was our model of the universe. And then Hubble comes along and screws all that up by measuring further away and stuff like that. So that was a really big deal. We used observations in many wavelengths to determine that we actually live in a barred spiral galaxy. So we no longer believe we live just in a spiral galaxy. 2005, I think, was our major confirmation that we in fact live in a barred spiral, not a spiral galaxy. Remember, a barred spiral is a subclass of a spiral, so it's still a spiral galaxy. It's just it's more barred than we had originally thought. This is a cool photograph, because look, you're seeing galaxies again in it there. But that's what our Milky Way looks like. And this, in fact, does look like the part of our Milky Way that looks like the center of it. So this is a artist's conception of what we think our galaxy looks like now. This is the M109 that I was just showing you. So you can see that's a very real photo of a real galaxy that happens to be in Ursa Major, and that is a barred spiral. And we think ours looks like that. And we have basically the barred spiral. What we found is that there's a Sagittarius arm, there's a Perseus arm, there's an outer arm, there's I think that says Noma, even though I'm not familiar with that one. It's Norma arm, maybe. And over here you see the Scutum Centaurus arm. That one I was familiar with. There's an Orion spur that we're actually in right here, and there's the sun. And again, I can't make out what this says. Oh, near something arm, near something. Anyways, so that's our rendition of it, and it was a major feat. Like I said, by 2005, we had the data that had it mapped out that we are in fact in a barred spiral, and it had several of our arms. So what we know about spiral galaxies, remember, is they have a disk, and that disk is a place where stars are created.
Can you explain that slide? Like, stars are in general are not concentrated in spiral arms, but then this concentrates hot young stars in spiral arms.
Yeah, gotcha. Yeah, that's actually confusing. So what you got to realize is the spiral arms are sort of, the bright ones are where star formation is occurring. Okay. And the dim ones are where star formation could occur because the elements happen to be present there for star formation to occur. And the bigger picture that you're probably not getting is the fact that the stars, unlike the spirals, the stars are actually spiraling around this. And as they go at different rates than the actual arms, they sometimes run from a dark area, which is non-star forming, to a bright area where the stars have been formed. And basically what's going on is because they're moving through that, they're running into a region where there's even higher density of gas and dust. And that highest density of gas and dust is star forming regions. Therefore, you find stars of all ages, but the only ones that are so short lived that they can't make it across the distance of that arm are the hot O and B stars. So the hot O and B stars are left there at any particular time, specifically because they were the only ones that didn't move far enough by the time you got to look at it. So the colder stars are continuing to meander through, and they get born, say, maybe like an orange star or G2V star like ours. They're born, and then they continue going on and travel around like this. Whereas the hot O and B stars look like they're not moving. They are moving, except their lifespan is so short that they don't make it any further than, say, across an arm. So we do have arms of interstellar media, molecular cloud stuff, and we look for that by looking for the 21 centimeter line of neutral hydrogen. And then when we plot those 21 centimeter lines, we find that they make arm shapes. And that's part of what was discovered by 2005. Also, when we plot O and B stars as well as ionized hydrogen, we find that they, in fact, those elements and those particular stars are actually found in other spirals as well. And those spirals, of course, would be the bright ones like this. So you can see sort of a dim little thing going around here. That's where you'd find the 21 centimeter lines, is in that dark spot. You'd find the O and B stars and the ionized hydrogen in this bright arm. Does that make sense? So stars in general are not concentrated in the spiral arms. Star formation occurs in spiral arms. This concentrates hot young stars in spiral arms. So they're all just sort of transiently passing through the arms, but the hot ones don't get to make it very far. So they're always still illuminating a particular bar, and that bar is more or less like a pressure or like a density wave of high density gas and dust. Here's that again, what I think is the Pinwheel Galaxy M101, I think it was. Spiral structures in galaxies are in galaxies because of disturbances in the disk as it rotates. The main thing is if the disturbance isn't continual or repeating, then that's not going to make an effect that lasts. So the fact that we have spiral arms that persist are indicative of disturbances that either repeat forever or are constant. A single disturbance, like I said, does not produce stable spiral arms. A repetitive gravitational disturbance, such as an elongated bulge, compresses dust clouds every time they orbit through it, and that leads to more star formation. It's hard to find the size of our galaxy because of dust. There is a lot of dust in our galaxy, so dust blocks light. Remember, all stuff in space are basically, when you're interacting with waves, anything that's, say, within a factor of 10 of the wavelength. In other words, if its size is almost 10 times smaller or its size is almost 10 times bigger, chances are it's going to interact quite a bit with that particular wavelength. If, however, it's markedly, it's 10 or bigger, markedly bigger, or 10 or like markedly smaller, then it's not going to interact with it. So the gas and dust, knowing what wavelength can't get through it, tells us what size the particles are, and that's how we're able to reach conclusions that it's dust and gas and stuff like that. But that dust blocks light, it makes things fainter, and in fact, it degrades the brightness so that sometimes you can get confused about the brightness and choose its luminosity to be wrong or choose its distance to be wrong. Okay. Now, Harlow Shapley actually is the one that started noticing we had a lot of globular clusters, excuse me, not open clusters, had a lot of globular clusters, and these things are huge, and they're weird in that they're in what appears to be a spherically symmetric shape around the center of our galaxy. And this was key because when he realized that they seemed to be oriented in a sphere or positioned in a spherical structure, he thought, well, that's kind of weird. I wonder where the center is. And then he put together the fact that the center should be the galaxy itself because that's the epicenter of all the gravitational strength, basically. So that's how we were able to conclude that we were about 27,000 light years outside of the center of our galaxy. Remember, our galaxy is about 100 light years across. And if you figure that, then the radius is about 50 light years, and then 50,000 light years, and then we're 27,000 light years out. So we're a little bit further than halfway. So we're like in the suburbs, if you will. So Shapley plotted their positions, and from this data, he made the first size estimate of our galaxy and discovered that our sun is not near the center, which is obviously a big thing, but it's also a continuance of the Copernican revolution. Remember, I told you the Copernican revolution is not only about Copernicus suggesting that we're not the center of the universe, or let's leave it at that. It is sort of more about the us not being the center of the universe and us not being special. So it's a continuance of that. I was just going, the reason why I was trying to change that was I was going to go into the spiel about the scientific revolution about the versus the Copernican revolution, but no, I just stick with the Copernican revolution and say, yeah, that this is a continuance of that, just like us being a leaf on the great tree of life that basically has all of us as distant cousins of every other living thing on Earth. So it's kind of neat to find that, yeah, the evidence did show that, you know, there's a center to our galaxy and we're not it. So that's what Shapley discovered. Globular clusters in the halo are older than the open clusters, stars in the disk. And in fact, what your book iterated is that, yes, open clusters can be quite old and globular clusters can be quite young. But the youngest globular cluster we've ever found is still considerably older than the oldest open cluster we've ever found. The globular clusters are normally huge and have, you know, hundreds of thousands, if not millions of stars. And we see them oriented in a spherical distribution around our galaxy. And in fact, we find they're very, very old stars, but they still have complex or heavy elements, if you will. So they're not just made of hydrogen and helium. So we know they're not first generation stars. They're at least the second generation stars. But the fact that they're remaining, they're in a spherical distribution. That spherical distribution has very little gas and dust around it, tells us that, okay, maybe these things were formed when there was a lot more gas and dust around, but something took away all that and left just our spiral disk and our little bit of a nebula, or excuse me, a little bit of a nucleus in the center. So globular clusters can be 13 billion years old. We see no young globular clusters. The processes that form the two types of clusters must have been very different. And this brings us to the chemical evolution part. Remember, the Big Bang created hydrogen, helium, and that's pretty much it. I mean, there is some trace amounts of lithium, beryllium, and boron, but generally speaking, it's hydrogen, helium, and nothing else, right? So all the other elements have to be created by stars. We've learned about low mass stars, and we learned that they do create, for instance, carbon, and they might even, if they're a little bit higher on the low mass end, they might even go a little bit further and produce some silicon. But generally speaking, that's about it. And they also don't have these huge explosions that distribute that material everywhere, whereas the high mass stars actually do go all the way up to producing iron. And then they explode in a supernova explosion. And when that explodes, that gives off all those elements they've made, including some of the ones that they've erased, which is like lithium and beryllium. But then the energy of the supernova is also high enough that other nuclear reactions can take place, ones that are energetically not favorable, and therefore going beyond fusion of iron. So when you fuse into iron, remember it was the energetic dead end of fusion. But in the supernova explosion, there's so much energy around that you can actually force iron to fuse and higher elements to fuse and create higher elements still. Even though it's a loss of energy, there's so much energy around, it just happens. So that's where all those elements come from. So whenever we see a star and it's, pretty much just hydrogen and helium, we think, oh, well, that was probably a first generation star. Obviously, it'd have to be very old. If we found a new star, for instance, one that's on the order of tens of millions of years old, we would not expect it to have just hydrogen and helium. We expect it to have a lot more, or we have to do some explaining about how it was, how it was sequestered away from all the other sources of elements other than hydrogen and helium. The more massive elements found in the star, the higher the amount of the prior star formation. So, that's just a rule. As like I said, the more generations of stars live and die, the more matter we have that's not just hydrogen and helium. Therefore, you have to realize that the more complex the star composition is, in other words, the more elements beyond hydrogen and helium, the older the gas cloud was that made it. So new heavy elements are ejected into space through supernova. New stars form with some heavy elements, and the abundance of heavy elements records the history of star formation. So, and that is the case. I mean, we could do statistical models about how frequently stars are created in our universe. What percentages of those stars are, 0.8 solar masses to 0.9, what percentage are 0.9 to 1, and so on and so forth, and then do all that work and then come back with a calculation. And we find that the elements present are pretty much in line with those statistics. So that's more evidence of not only the Big Bang, but also nucleosynthesis as put out by Fred Hoyle. So that's kind of a really big deal. We observe that younger stars have greater abundance of heavy elements than older stars, and globular clusters can have as little as 0.5% of the amount of heavy elements that disk stars like the sun possess. So the globular clusters are very, very old, but the fact that they have anything beyond hydrogen and helium says they're not first generation. So the abundances do vary throughout the disk. Abundances of heavy elements vary. In fact, what we find is the inner disk has a lot of abundance of a lot of elements beyond hydrogen and helium, and the outer disk has less. The relatively old stars are near the center of the disk. So the center of the disk has old stars, which sounds kind of contradictory, but they're not the same thing. Remember, it says relatively old stars are near the center of the disk, and the younger stars are near the outer edge. So they're talking old stars are right in here, younger stars are out here, but the old stars have abundances of heavy elements. So that sounds kind of weird because they're old stars, but what they're meaning is that this is a rapid star formation areas in the inner disk, and therefore it's had a lot of turnover. So it's had a lot of generations come before it that created the other elements, and it still has the oldest of stars. Remember, if you make a star at 0.8 solar masses, which is really the bottom limit of how long or how small a star can be, we project that the life of that star is actually older than the universe. So we don't, I don't know what just happened. So we don't think that any 0.8 solar mass star that's ever been created has ever died. So you can imagine if, statistically speaking, some of the stars that were created in our Milky Way were most certainly a 0.8 solar mass star, and not a single one of them have died. So that alone could, in some sense, explain the fact that you have old stars. But you have old stars, you also have abundances of heavier elements, because the younger stars that were born in that area have since died and given up their gas to make the heavy abundances. The sun has about 2% concentration of heavy elements. Even the oldest globular clusters have a small amount of heavy elements. Again, that's the argument saying that it's not a first generation group of stars. There must have been at least one generation. There must have been at least one generation of stars that existed prior to the globular clusters to process those elements. Those stars would have been very massive and therefore would have died quickly. astronomers have not observed the first generation of stars. We've never found those first generation of stars. That would be a really wonderful boon and another wonderful feather in the cap for the evidence of the Big Bang and nucleosynthesis, but we have not observed that yet. But remember, we don't necessarily expect that to be the case, because the lifespans and the lifetimes that we were talking about with high mass and low mass stars were in the presence of basically all the masses and elements and stuff that we have. The earliest stars, we're not really completely sure how they would have come together. And if they come together by a slightly different mechanism, like did stars form first and then galaxies, or did galaxies form with bunches of clouds of gas and dust and then they made stars? That's a big issue. And then what precipitated all that, you'll learn in this chapter, you'll start to learn it. Dark matter had a big role in that. So what role did that play in terms of the individual stars, so that the first generation stars might not have lived like the generations of stars that we've learned about as low mass and high mass stars? And if they all died, or if they were mostly supermassive, then they would die rather quickly, and we wouldn't expect a single one of them to be alive, to still be fusing hydrogen and helium. If any of them were around the 0.8 solar masses, we'd expect them, but we've never found one like that. Does anybody have any questions, or does everybody understand that, I should say? Whoa, I don't know what I just did. Okay. So our galaxy has a thin disk and a thick disk. And the thicker disk, which is about 3,700 parsecs thick, remember 3,700 parsecs, you got to multiply that by 3.26. And from that, you would get roughly, what, 11,000 light years thick. And then this from here to here is on the order of 100,000 light years. So 11,000 to 100,000. Your book made a point to mention that this is about the thickness of a CD compared to the diameter of a CD. Okay, but it has a thick disk, and then it has a thinner disk that's right along the center. So the thicker disk has older stars with ages greater than 8 billion years. That's above and below the thin disk at the center. And then the thinner disk, which not only is at the center, but extends way beyond, is actually younger stars with ages less than 8 billion years old. There's a bulge of older stars in the center, and then this halo portion. So remember, spiral galaxies have a spherical portion and a disk portion. The spherical portion is called the halo, and then the central bulge, and then the disk portion, of course, is just the disk. But when we talk about the spherical part, we're not only talking about the bulge, we're also talking about the halo of it. And it turns out our halo are actually the oldest stars, which have ages around 10 billion years. And notice the globular clusters are way the poop out here. So that's where all the globular clusters are. This is a picture, I would think it might be in the infrared. No, it couldn't be the infrared. Yeah, anyways, let me find out what that picture is in. I hate it when they do that. They put a picture and they don't tell you what wavelength is in like they do in the book. But I'll look at it real quick because I forgot to look that one up. That one is Milky Way observations, Gaia satellite. Oh, yeah, they didn't explain it there either. Normally they put that little spectrum under the photograph and then they mark off the part of the electromagnetic spectrum that it came from. So dust is also concentrated in the plane of the galaxy as seen in the recent image from the Gaia mission. I would suspect, since they're talking about gas, I would suspect this might be in the microwave region because, you know, well, actually, they did say gas, not dust, didn't they? Or did they say dust? Yeah. Oh, they did say dust. Yeah, so maybe on the higher wavelength end. So I would say maybe in the microwave, the microwave or radio region. So anyways, that's an actual photo. Now what you're seeing here is an all sky photo. So this edge is supposed to be the same as this edge. So we're looking at the entire expanse of the disk of the Milky Way over 360 degrees, and we're looking at that. Okay. Now what we also find is there's components of the halo, and here's our little itty bitty Milky Way galaxy, which is 100,000 light years across. But you look out here, and there's this giant halo that's even bigger still, and you can tell that's on the order of 10 times the size, and maybe even 20 times the size. So the halo is divided into three parts. It's got an inner halo, an outer halo, and a gas halo. The stars in the halo have random orbits that take them out of the disk. So stars in the halo can do this and that and this and that and all that good stuff. They're all moving in every which way, not unlike what happens in an elliptical galaxy. And so they have sort of random directions, random velocities, and because they're so far out, they're not interacting so much with the disk, at least in these outer parts, so they're not likely to settle down into the disk. Some of these stars near the sun are called high velocity stars because they have high radial velocities, or what we call proper motion. By the way, that radial velocity or that proper motion is how they appear to move across the sky over centuries, for instance. That's another way we can use to tell how far away things are. Stars in the outer halo have lower fractions of heavy elements. There is a large halo of diffuse X-ray emitting gas. So this gas out here is really super hot, but it's also weird in that it's super hot. It emits in the X-rays, but it wouldn't burn you. Sort of like sticking your arm in an 800-degree oven, unless you touch parts of the oven. It'll feel warm, but it's not actually going to burn you. The same thing here is because it's so diffuse, the actual particles that are moving so rapidly, which is the definition of high temperature, they're not actually likely to collide with you very much. So they're not distributing much energy to you. Hence, it doesn't burn you. But yeah, this stuff is literally on the order of hundreds of thousands and millions of Kelvin. So that surrounds our galaxy. It turns out magnetic fields play a bigger role than you might think, especially when you consider that the magnetic field that we run into around our galaxy is really pretty minor compared even to the magnetic field strength of our Earth, but it's still very important. Cosmic rays, which are charged particles moving close to the speed of light, they can have super high energies, like they might range from a few tenths of the speed of light, say 0.1 or 0.2 C, but they also run up to 0.999999 times the speed of light, or times C. So they actually can be very, very fast. But these dense molecular clouds, remember the molecular clouds are basically star-forming regions. They can actually hold quite a bit of matter in there, and they can hold some ions, stuff like that. But magnetism can sort of get caught up by a magnetic field, say, running along it. If it happens to be in the dense molecular cloud, which are mostly aligned along the central disk, then that magnetic field will be held within that molecular cloud, just like magnetic field lines are held within an iron rod. So once you find something that's quote unquote magnetic, like ferrous material like iron, then it's likely that any magnetic field lines that cross it are going to stay in it. And in fact, that could actually force them to come closer and closer together and increase the magnetic field, which is why when you wrap a nail with current carrying wires, it becomes a pretty strong electromagnet. So the sort of same thing's going on here. Then between molecular clouds, the magnetic fields try to do their weird thing and spread out and stuff like that. But again, they're going to run into another molecular cloud that can hold them in as well. But the radiation coming from it gets trapped because the weird force law, it's called the Lorentz force law, but basically the force law that dictates the forces on charged particles moving around the magnetic field says something odd. Let me escape from this for just a second. I'm going to stop share. So there's this weird rule that basically if you take the velocity of a charged particle, if it's a positive charge, you just take the velocity. If it's a negative charge, you point it the opposite direction of the velocity. So it's if it's going this way and it's negative, you pretend like it's going this way. But you take your index finger and you point that in the direction of the velocity of the charged particle. Okay, and you got to use your right hand. Now you take this finger right here and you hold it at a 90-degree angle. See how that's a 90-degree angle to my index finger? That's supposed to point in the direction of the magnetic field. So like those magnetic fields that we were seeing in that diagram are doing this. So we'd want them sort of pointing like this. And then lo and behold, this third finger, which is also perpendicular to the first two, see, that thumb is the direction of the force. So as a particle, say, moves this way, if a magnetic field's this way, then it's going to tend to feel a force this way. So that's actually going to cause the particle to spiral up. But the magnetic field hasn't changed. That's still pointing that way, so it's going to spiral around. And lo and behold, what happens is particles spiral around magnetic fields, either this way or that way. And that's what they're showing here, is the synchrotron radiation, which is, remember, I've mentioned this before, anytime a charged particle accelerates, it actually gives off radiation. And in this case, since they're obviously going in a spiral or a helix shape in this case, they're actually producing radiation because they're accelerating, and they're accelerating because they're going in a non-straight line. So anytime you change, even turning your steering wheel, remember, is accelerating. You don't have to speed up or slow down to accelerate. So that's causing synchrotron radiation. And that actually corrals, if you will, that actually corrals the magnetic field lines and the synchrotron radiation, and keeps it around there. So now that I've explained that part, let's go back to the slide. And let's do the slideshow. So it's pretty, seriously, I want to do a slideshow. There it is. Come on, come on. Okay. So cosmic rays can have very high energies, but they are trapped by the Milky Way's magnetic field. So they end up staying mostly within the disk. When they spiral around the magnetic field, they produce a synchrotron radiation and the rotation of the Milky Way. So here's sort of a Doppler shifted picture of the all sky around us. And you can see sort of the disk of our Milky Way galaxy right through the middle. But you see one whole side is red and the other side is blue. And then there's some intermediate stuff in between. That's because we're not, if we were at dead center, then exactly half of this would be red and the other half would be blue. We're a little bit out to the side, and what we're seeing is you can sort of interpret this red as red shifted, which is stuff moving away from us, and this blue is blue shifted because stuff is moving towards us. So when we look in the direction, in this direction, we actually see gas clouds moving away from us, right? Because we're, say, right here, we're moving this way. Anything going this way is going to be moving away from us. That's red shifted. And looking in this direction, we see gas clouds moving toward us. So if we actually look, say, down this way, we can actually see the gas clouds coming towards us, so on and so forth. But neutral hydrogen is what we use to map out that stuff. Remember the 21 centimeter line, which is from the electrons being parallel spin with the nucleus versus the electrons flipping upside down and being anti-parallel spin with the nucleus. That creates the 21 centimeter line, which is well within the microwave/radio part of the wavelength. And because it's that big, it's not going to interact with things unless they're around 20 centimeters in size. So basically a 21 centimeter line only gets blocked by things that are comparable in size to 21 centimeters, maybe as small as 2 centimeters or 2.1 centimeters, and maybe as big as 200 centimeters. So we use the shifts of this line to determine the orbital rotation of the disk. When we do that, we can then use our Doppler shift formula for the velocity. And what we find is, unlike Kepler's law, which suggests that this should reach some peak and then fall off like this, this comes down and then starts to level off and then starts to climb back out again. And in fact, by the time we get to the Large Magellanic Cloud, it's still quite level. So what this suggests is that the further you get from the galaxy, from the center of the galaxy, does not mean the amount of matter is getting smaller. In fact, the amount of matter between you or your particular spot and the center of the galaxy is actually increasing. So because of that, we make the conclusion that there must be more mass than what we're seeing. And that is how we infer the existence of dark matter. Now, since then, we found a lot of other evidence that's also consistent with it, and we're no longer at a point where we can say, well, maybe we just got our gravity wrong. No, we don't. We don't believe that's the case. The dark energy is sort of in the same part of argument now as well. So when we learn about dark energy, you'll see that that's another scenario. We don't think that's another example of us getting our gravity wrong, but that one's not quite as solid ground as this one. So the flat rotation curve really suggests that about 90% of the matter in the Milky Way is dark matter, and it's spherically oriented around the Milky Way, not mostly in the disk like our luminous matter is. So we also find that when we look towards the Sagittarius constellation, there's something we call Sagittarius A star. That is what we think is the black hole at the center of our galaxy, which is about 4 million solar masses. And when we see that, we see things that do some crazy orbits around it. And those orbits are super fast, and the object's really not bright enough to suggest something as big as, for instance, a 4 million solar mass star. So we really have to conclude that it is a black hole. And not only that, we get X-ray and gamma ray emissions that are coming from the disk that is basically the accretion disk around the black hole. So there is, as best we can tell, a black hole at the Milky Way center, revealed by stars nearby orbiting it quickly. The gas orbiting or falling onto the black hole produces both X-rays and gamma rays, and the black hole, like I said, is millions of solar masses. In addition to that, we also see jets, symmetric jets that shoot above and below the disk of the galaxy. And in fact is X-ray and gamma ray emissions that we expect to come from black holes. And these are on the order of 15 kiloparsecs, which is like 15,000 parsecs, but that's also like 45,000 light years. So these things are really comparable in size to half of the radius, or to the radius, if you will, of our galaxy. So those bulbs, if you will, are quite large. When we actually go to plot out the galaxies that we know of, what we found is there are groups of galaxies, which is the smallest size thing that is an assemblage of galaxies. It's called a group, and they usually have on the order of dozens or several dozen galaxies. In our case, I think we're looking at 40 or 60 different galaxies, and you can see them plotted here. The Milky Way being as if it's the center of the universe, because to us it essentially is. Actually, we're a little bit off center on it even, but still. The nearest, of course, galaxies to us are, we see Leo 1, Leo A, Leo 2, the Canis Dwarf Galaxy. You can see the Andromeda Galaxy. That's the largest major galaxy. The second largest galaxy is Triangle, or actually I should say the second largest after us, Milky Way and Andromeda. There's still a little bit of debate of which one's more massive. I think the last we heard, Andromeda's a little bit more massive than us, but the third largest is really the Triangulum Galaxy, but you can see that is considerably further away than the Andromeda Galaxy being 2.5 million light years away. But you can see these are just the galaxies of our local group, and we think, though it's not completely certain, that they're all interacting with us gravitationally. Some could actually just be passing through, right? And they might have enough velocity where they're going to pass through and not be captured by our group. Whoa. They may have enough velocity that they're going to pass through and not be captured by our group. But that's the kind of thing that takes, millions of years to watch and see play out. So we don't know what fraction of these are really part of our group and what fraction of these are just passing through. It turns out that galaxies, compared to the distances of separation between them, are way closer together than, oddly enough, the stars are close together within the galaxies. So remember how I talked about how space was mostly empty and blah, blah, blah. The likelihoods of something running into something is very slim. That's definitely the case, even when, Milky Way, which will seemingly run into the Andromeda Galaxy in about 4 billion years, even when they run into each other, we're going to have gas and dust being stripped away from the two of them, and out will pop probably a couple of spiral galaxies, specifically because they've lost their gas and dust. But it's probably going to be a very small number of actual stars, planets, or objects that ran into each other. In other words, big structures are probably not going to run into each other very much, if at all. Again, that's because the relative space versus size of things within the galaxy is the space is way bigger than the sizes. But when you're talking about galaxies, they run into each other all the time because the space is not that much bigger than their sizes. The local group, which has two giant barred spirals, that's Andromeda and us, actually Triangulum and us, and a smaller spiral and several dozen dwarf galaxies. No, I think maybe we have concluded that Andromeda is a barred spiral. Yeah, it's. I'm not up on that reading. That's something that they might be referring to here. I should.
Isn't it?
Yes,
Yeah,
sir.
isn't it a barred spiral, but just like
Big.
way bigger than us?
Thank you. I don't remember reading that, but yeah, that seems to be what they're pointing to because they said the smaller spiral. That must be the Triangulum.
Aren't spirals and like barred spirals rare in general compared to like ellipticals and stuff?
Yes, yeah, they're normally way more massive, and I mean, occasionally they can be bigger and often are bigger in physical dimension, but not in mass. But yes, okay.
Oh,
So the
not
Milky Way. Go
size, I
ahead.
meant like rarity.
Oh yeah. That's exactly right. Yeah, spirals are way more prominent. Ellipticals, I think irregulars are almost as prominent as spirals, and then elliptical are least prominent. And we'll learn that more. I think it's in chapter 22, maybe 23, but I'm pretty sure it's 22. So if we go, whoa, I did some crazy stuff there. Okay, so groups and satellite galaxies. So Milky Way probably formed by the merger of many smaller proto-galaxies. Several of these are still orbiting the Milky Way as satellite galaxies, and the Sagittarius dwarf has been disrupted, leaving streams of stars. So basically, when they collide, our models show that mostly the gas, the dust, is what gets ripped apart, and the gas sort of stays with the gravitational center, if you will. So a lot of the stuff that we see where there's dust left, but not or gas left, but without dust, we think that's due to collisions. That's why we think spirals are sort of one of the end games ellipticals are one of the end games of spirals running into each other. So here's a picture of the large Magellanic Cloud and the small Magellanic Cloud, which if you're in the southern hemisphere, you can see really prominently right next to the Milky Way. It's kind of nice to check that out. I've been below or close to the equator, but never quite seen it. So that's kind of a bummer. The Milky Way offers clues to galaxy formation, not only our own galaxy, because obviously that's what the data we get, but the other thing is, remember, the cosmological principle says that all particular spots in the universe are about the same, and all particular directions in the universe are about the same. So we wouldn't expect galaxies to form significantly differently in other parts of the galaxy unless we find a bunch of different formation techniques in our own part of the galaxy. And this seems to be the case. The Milky Way says that all halo stars have some heavy elements, so at least one prior generation of stars must have existed. Since the halo stars were created from gas, they were formed before interstellar gas was all concentrated into the disk. In other words, they would have had dust in there too. And later star formation was all in the disk, and that's what we're seeing now. So we can see sort of over time that basically there's a progress or an evolutionary process, if you will, that galaxies go through, not only by collision, but by creation. And part of their creation can be collision. Currently, what we think is dark matter played a huge role in the first galaxies forming. So you can check out that. This is the process of science. I always recommend you read over these things, even though I never read them myself for the class. I always read them when I get to them. But here's the working it out mathematics stuff. Anybody interested in the math, you can see how that all works out. Check your understanding questions are in there. But that's basically it. We've now finished chapter 20. I'm going to stop share and take questions and then let you guys go. So in fact, anybody that doesn't have any questions, remember we've got, tests and practice tests that you need to keep aware of. You got homeworks you got to keep doing. Let me know if you have any problems with anything. But other than that, everyone's free to go unless they have questions.
You're gonna open SmartWorks 20?
Oh yes, I thought it was already open, but yes, I'll
You-
double check. Make sure
Only
it's open.
19's open.
Oh, okay, gotcha. Thanks for letting me know that. I'll definitely go ahead and open the rest of them.
Just go ahead and open all of them.
Yeah, that's what I'm gonna do now. Let's see. I can go not there, not there. Oh, there I am. I'm trying to go to the part. Oh, there it is. My modules for my astronomy course, and then I go to my astronomy course. Hopefully, I can get into SmartWork. Anybody else have any question while you're here? Have a great, safe weekend. And I'm going to change these opening dates to now. God dang it. I hate it when it does this. Let me see if I got another browser open somewhere. There you go. That'll work. I've got my password saved in one browser, but not this browser. So now I got to go back to Google Earth. I mean, Google Earth. I got to go back to Google Chrome.
Google Earth.
Google Earth. My name's Billy.
Stop recording.
Yeah, for real. I'm going to get in trouble. Let's see. Continue in your miserly ways. Okay, I've stopped recording, so